लिसन। हाँ सुजीत, आपको सुनाई दे रहा है?
यस सर।
ठीक है। Okay, so my assumption is that you must have gone through or have tried to revise dynamic programming. Dynamic programming means that what is your problem? You have big problem. Oh no, your problem size may be big or may be defined over some n elements. Is it a way, there is a way by which you can break your big problem into a smaller size instance? So initially maybe you are sorting over n elements, later you say that, oh, if I sort it over n by 2 and n by 2, so same problem but being devised or defined over two sub problems. So this can also be seen as a dynamic programming problem and the divide and conquer. But the difference between both of them is that divide and conquer one breaks things into two parts. Both of them, the solution of both of them are independent to each other. They are not related. But in the case of dynamic programming problem, when I divide big problem into a small problem, all these small problems are related to each other. If they are related, that's dynamic programming, else it is a divide and conquer strategy. Essentially, we try to find out, but is there any optimal structure? And if we know that optimal structure on that small problem, we keep on building the solution recursively on the bigger problem and so on. Let us see a very simple example. I'm just giving this just for the sake of completeness. Anyways, most of you are maybe definitely being aware of this thing. So if I say factorial 5, you don't know the value. You will say, you give me factorial 4. Then I say factorial 3, even you don't know. Factorial 2, we don't know. Then we got factorial 1. And now you say that this value is equal to 1. What is this value? You say that 1 multiplied by, basically, sorry, it's going to be 2 multiplied by factor of 1. This is going to be 3 multiplied by factor of 2. Anyways, it's going to be n minus 1 factor of n. I'm sorry, n factor of n minus 1. There is some optimal structure which was being there. That's why you can write it in the form of recursion and then you keep on solving. We will come back that how we can use such an optimality to, instead of approximating, instead of computing, can we approximate it? Why do you require approximation? You will come back to it. But the optimality structure which is going to be required or useful will be that right now I am having Komal with me. Komal abhi idhar aa gaya mere paas, sitting in front of me. So if any one of you is available in the campus, you can come and join the classes over here. Yeah, so now I am saying that instead of doing this thing, can I predict? I say that, Komal, can you tell me F5? He is saying, okay. F5 is 22. Is it right or wrong? I don't know. But Komal is right now predicting for me. He is not using recursion. Why? Because recursion is very long. It's going to take huge amount of time. He wanted to develop some ability by magic or so. We'll see that how it can be done. But let us first so let us first understand that. Let us first understand what is going to happen is that our F5 is also equal to the predicted value, and sorry, it's not 4. 5 times factorial of 4. So Komal is saying that factorial 5 is where is it? Yeah. Factorial 5 is 22. There is another way by which I can get the value of factorial 5. What is that? It is 5 multiplied by factorial 4. Now, who is going to tell me this factorial 4? Again, Komal. That is the optimality. I'm assuming that if you are telling me correctly, your solutions and your answers need to be consistent within yourself. So something you predict and something I utilize the optimality. So I will again ask factorial 4. He will say 20, then it is 5. That's 100. It's wrong. So how far these two things are, that is going to be maybe utilized to train these upcoming networks. Okay. Yeah. So the point is that TV is actually creating some issue and keep on restarting multiple times. So we will somehow manage. Don't worry. You cannot do much into this. You'll have to somehow manage. Yeah, wait. Can you see Daksh is there? Ranjit. Okay. Any questions so far? Not maybe not everywhere, but at least just your previous things need to be consistent with you. Here your previous thing is 4. Suppose that you are a student. Komal wanted to say, hey, sir, I'm a I'm a very good cricket player. Then I'll ask 5 more guys who are just immediately connected to you. If they also say the same thing, if it is consistent, know how far you are. Because your prediction is wrong. Because if it is right over here, this thing also need to be satisfied. Understood? So this is the thing that we are going to be utilizing in our deep Q learning. How far you are from you are predicting. And then what is this step? This is the recursion step that is actually coming from the Bellman optimality. I'm asking that from India, you want to go to America. How much kilometers it is? You randomly guess something. And I will say, okay, tell me from here, Delhi distance is this. Now tell me from Delhi, how far it is. Then you say something, I add both of these things, it has to be equal. So that is something that is unsupervised, you can see. We don't know any answer. We just see how consistent you are in your prediction, utilizing the optimality condition, which essentially means that if this is correct, this also need to be correct. Okay, so with this letter, so that is the thing that we are going to use as dynamic programming part. And that is what I have said, that please read 1 or 2 dynamic DP algorithm. One is Bellman-Ford shortest path algorithm. So I assume that you all are now must be aware of this. If not, please refresh it because it's going to be helpful. Only Bellman-Ford algorithm or any other DP, whichever you are in, interested. Okay. Now, so in last lecture, what we have seen that we are going to have a policy. Now, once you know a policy, you require a way by which you can somehow, if I say, by which you can somehow evaluate that policy. Can you evaluate it properly? So how can we evaluate? That is something we are going to understand. So what I expect is that all of you are going to use your copy and pen. and one by one, this whole figure is in front of you. Numbering is being written 1, 2, 3, 4, 5, 6, 7, 8, and so on. And I will be explaining one by one what is happening. So, before that, what is the meaning of the evaluation of a policy is that under this policy, what is the value of any state? Under this policy, what is the value of this state? Because if you know that given this policy, this is the value of the state, and for all the states, if you know the values, that's the value function, you got the evaluation of that policy. Now, for that, we first take policy as pi, value function as v, policy fixed, value function v s is going to tell the value of state s. But it's also the case that v1s, v2s, v3s, what does that mean? It means that I am iteratively trying to converge to a proper value function. Initially, some random value function. Then v1 is slightly better than v2. v1 is slightly better than v0. v2 is slightly better than v1. In fact, vk is slightly better than vk minus 1. What does that mean? So if I have a state, I have a v2 function right now. With this v2 function, I ask, hey, tell me the state value of state s, that is v2s. May not be correct. I do something and find out v3s, which is better. What does that mean, better? More towards the real value function, because our real or actual value function is completely different. May not be the same in which we are now assuming that it is. Every time this is happening, what you can do, Preeti? HDMI 1, you can sit over here, because from here only you can do. You'll have to choose these guys up and down and so on. It may keep on creating some issue. Okay. Now, Deepti, Prashant, do you have any issues, Deepti?
No, sir, not till now.
Sir, some issues are happening in here because of the TV, but don't worry. Okay, 1, this is policy. 2, we are trying to compute the value function, or in fact the value of my state s. But k plus 1th iteration. So you understand that value function is some function not known to us. We are trying to estimate in the best possible way using our recursive definition that we have seen, that vk or vk plus 1 is going to be derived from vk, at state s. So this is the thing that we are actually looking how to get this using vk. If vk is known to you, how vk is known? Random. v0 is some random, then v1, then v2, then v3, then v4, and so on. And it's being shown that if we apply such recursive module using the recursion, it's being proven that it is definitely going to be converged and very near to the actual optimal value function. Okay. Policy 2, this is the thing that we are looking for using vk. State is s. Where is the third number? Oh, this is the vk, right? Third. Where is fourth? This is fourth. What is this policy? state to action mapping as per the policy, which is nothing but this. What is pi? Pi is just telling you that for this state, this is the action. 5. So this is my state S, by the way. Okay. With this state, I mean, it's very, very simple. I have written each and everything just for the sake of completeness. State S. I can take action A1. I can take action A2. If I take action A1, I'm going to get a reward of, this guy. If I take this action, I'm going to get a reward of this guy. RSA2, RSA1. Now, at this state, if you take this action, this reward you are going to get. But you are going to end up to which state? Who is going to tell you? Chinmay Patil, can you tell? Chinmay Patil.
Yes, sir.
So at state S, if you take action A1, which state you are going to land up? Who is going to tell you this?
Sir, MDP.
MDP, environment. Okay. So basically, environment is going to tell. Ab aap mute kar lijiye, Chinmay. Yes, Chinmay. Yeah. So environment is going to tell which is being embedded or designed as an MDP, which is having your probability, transition probability. That is this. That probability of S1 A1 at state S taking an action A1, you are reaching S1 by this probability. Same thing, probability at S, you take action A1, you will reach to S2. You reach S1, you have reached S2. You may reach S3, you may reach S4 with these probabilities, right? With these probabilities. Now the point is that this reward is basically going to tell you that if at this state, I'm coming on to this, but somebody may ask, on this state, if you take A2, what is the reward that you are going to get? This one. But that was being defined how? It was being defined as R, S, S dash, A2. That at this state, if you take this action, what is the total reward that you can get? But it is being defined as that here, if you take this action, you may end up over here, you may end up over here with different probabilities. So basically, you may get either this reward or that reward, depending upon the probability. Maybe if it is 0.5 and 0.5, then the average of both of this, if it is 0.6 and 0.4, 0.6 multiplied by this, 0.4 multiplied by this, and so on, weighted. So, by the way, you can see S state, then you can see S1, S2, S3, S4. I wanted to know the value of Vk plus 1 S. For that, I am going to use the Vk, kth iterations value of S1, S2, S3, S4. This is Vk S1. For this, you will be Vk S2. And don't forget what is the meaning of Vk or V of S2. Under such a policy is fixed, by the way. Understand, policy is fixed. Value is keep on changing. Value function keep on changing. How? V1, V2, V3, V4, V5. After some time, you will get the best possible or the actual thing. Policy is fixed. After 20th iteration, you get V20. And if it got converged, not changing, what does that mean? That's the optimal one. Under this policy, if you start from S2, that is the maximum that you can get. Initially, it is wrong. Maybe V1 is wrong, V2 is wrong, V5 is wrong, and keep on iterating slowly. Okay, so what is this value? VKS1. What is this value which we are saying VKS1? VKS1 is very simple. Can I do it like this? And I will show you maybe for one. So this is the path. You see, this is one path. First, you are getting this guy. Anyways, you are not getting this. It is saying that this is the consolidated thing for both of them. But essentially, what is the reward that you will get once you go from here to here? SS1. What does it mean? From S, you have reached to S1. Taking an action, A1. What is the definition of the reward? This is the definition of the reward, which you have got plus the probability, basically this one, because every time you are not going to come over here. You're only going to be coming over here in this much, with this much amount of probability. Because even at this state, if you take this action, 100% you are not coming here, only these many probability, these many times you are going to come over here. Multiplied by VKS1, because this is the value VKS1 that you are getting from the kth system. How you have got this? You have got this because k equal to 0, you are initializing, and k equal to 1, you are going to use that V0 initialize thing. K equal to k plus 1, you are going to utilize this k. So this k is known to you. We are directly using it. You just remember that factorial 4. So this is, we are going to utilize, by the way. This is the probability by which it is going to be in this landing in onto this state. If you have taken action A1 at state this. So this is the total amount that you can achieve. But at state S, how many times you are going to take an action A1? Who is going to tell you? Policy. So this is the probability by which at state S, you are going to take an action A1. Now let us reiterate the whole thing again. Very simple. At this state, with this probability, you will be going over here. With this probability, you will be going over here. With this probability, if you reach here, then what? With this probability, you are in this subtree. Within that, with this probability, you will be over here. With this probability, you will be here. How much amount of reward you are going to get if you reach from here to here? It's very simple. What is that? This thing plus the value of this. But every time you are not coming over here, so multiplying with the probability. So this is the value that you can get. But only these many times you will be allowed to come over here. So that is why it got multiplied. No, Komal, you ask.
Yeah, yes, sir. Actually, if we are calculating pi a1s, then suppose pi star a1s is more greater than pi a1s, then this will no more, I mean, dominant in this.
I mean,
so suppose the first term is more very high. Suppose it's 5 and this is 3, and for the other S2 state, this is 3 and other is 3. And this is better than. We are not only dependent on pi a1s. So we were looking for pi star.
No, the point, let me tell you, the point is that the value at this is not only coming from this, not only from this, not only from this, not only from this. It is coming from all of them. Why? Because this is being dependent upon all of them, right? But with different probabilities. With this probability you are coming here, with this probability you are coming here, with this probability you are coming here, with this probability you are coming here. So essentially all of them need to be weighted sum. Who is doing this weighted sum? These probabilities are doing these weighted sums. So this is first, that within this thing, how much is coming over here, how much is coming from here. He is saying, hey, I am giving VKS1. I'm saying, hey, you cannot give VKS1. With this probability, I'm going, so multiplied by this. He is saying, hey, I am going to give you VKS2, multiply by this. Then you add both of them. But this guy is saying that this multiplied by this, plus whatever be the, the reward that you have got from here to here. Because this is the value of this. That is the value. This is the value. This is the weighted of this guy. Because you are coming here, this is the reward. But with not every time you are coming over here, only these many number of times.
So we are adding reward of SS1 with, I mean, probability with weighted probability. So how we can add?
I'm telling you. Why we are adding, we know why we are adding, because at this state you don't know you will be getting things from here or here or here or here.
But sir, it may be possible that different. We know that they are scalars.
So we are getting the expected value, na? Average value. Suppose that I am the one who is getting 4 things from 4 guys. Sometimes I ask you, sometimes I ask her. I am asking more, 70% you, 30% from her. So whatever your response multiplied by 70, whatever her response multiplied by 30 is the total response that I am going to get. Because you are looking for a stochastic process. It is not that it is coming from this or this. When you play an episode, it may be that definitely at this state you may have taken this thing and this thing and this thing. So that will be a deterministic single path. True. But you are not computing only for that guy, that episode. You play thousands of episodes. And the expected value. Sometimes you may be going over here, 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 depending upon these probabilities. And that is why you wanted to add, accumulate all those things. By the way, can you all see that B2 is going to be this? B2, or if I say that the reward that I am going to get from this path is this. That is the reward. That is the value of this state, but full thing cannot be seen, got multiplied with the probability, and with this probability, you are selecting that path. S1 and S2 both are being selected via same thing, because policy is saying the same policy value. But the other things, it will be pi A2S and pi A2S. Value S3, value S4. Corresponding reward and the corresponding state transition. You have got 4 values. Finally, value of S. k plus 1 is equal to a plus b plus c plus d. Why it's not averaged? Averaging is being anyways being done. So we can write it maybe in this form, which is slightly more complex. Please write it down. V k plus 1 s is equal to, for all actions, because I have shown only two actions, A1, A2, there may be multiple actions. For all actions, what you are going to do? Pi as. So if it is A1, then pi A1s, A2s, A3s, for all of them, multiplied by RSA, you understand, because that's the reward that you are going to get, plus gamma. There I didn't have used gamma because just for the sake of easiness, but you know that this guy S1, S2, whatever, they are not going to be directly contributing. They will be discounted and then contributed. So gamma times all the states S dash to S, and this probability. So this can actually be written like this. It's not much important to really say. It's a closed form function. We're not going to use that much. But the only thing is that Vk plus 1, what is that Vk plus 1 for all the states? It's a vector, state 1, state 2. If you want me to write it down, it can actually be for state 1, state 2, state 3, and so on for all the states. And that's the corresponding reward. That's the gamma which is fixed. And this is going to be multiplied. So you see that the exactly same thing is being replicated over here. This is for one state. You jam it and make it state 1, state 2, state 3, state 4. You will get a closed form matrix solution. So you have got V0 initialized. And from V0 you compute V1, from V1 you compute V2, from V2 you compute V3, from V3 you compute V4, and keep on doing. And it's being proven that if you utilize these optimality conditions, because we are doing all these things in the form of optimality, it is being shown that it's definitely going to be converged, and not only being converged, it's going to be converged into the optimal solution. Okay.
Second term will be matrix or it will be Harman product of probability of P.
See, this is having all the transition probability. This is having the corresponding VK. So this is again a point by point multiplication. Hadamard. One is called as, what do you say? One point by point multiplication. Hadamard. You have a math, huh? Math, so they used to say it as this. In MATLAB, if you take two vector, multiply m cross n, m cross 1, and other thing is also m cross 1, then it's a Hadamard. So you are going to get m cross 1, else it won't be multiplied. Chaliye, don't worry if you don't understand all that stuff. Anyways, I assume that all of you must have understood. But let us do it for a small problem. Policy evaluation for a small grid word for 4 actions. You all remember our old small grid word. This is small grid word. 16 things are there. 2 places are terminal conditions. 1, 2, 3, 4, 5, 6. If I place you anywhere, you have to find out a way or strategy by which you can move out as fast as possible, reach to your terminal state as fast as possible. Pi north, pi south, pi east, pi west. Dot means any place at any location. If you wanted to go 0.5, 0.1, 0.25, which is 1 by 4, it's a random policy, which is saying that at any location, you wanted to go to any direction, it's a uniformly random. What does that mean? Mean that you can go here, here, and here, any direction with the same probability you can go. Reward is anyways -1 because as small as number of steps you are expected to take. Right now we are utilizing undiscounted MDP just for the sake of completeness. Gamma is equal to 1. How long does it take to reach some terminal state from a grid point? We need to compute the optimal policy. Most other things are known right now. I am going to do things for you. You need to spend some good amount of time and understand. If you understood this, everything is okay. T, all those things, value functions are being written. V0, this is your V0. This is your V0. Not a good value function. We have initialized with 0. We don't know. V0, 1 is 0. V0, 2 is 0. V0, 3 is 0. All of them are 0. Achha. What is the meaning of this? V0i denotes the number of steps required to move from the state grid to a terminal state T. Value function is telling what's the difference between a value function and policy. Policy is just telling where to go, what action to take. Value function is telling how good or bad a state is. What is your policy? Random. What's your value function? Randomly initialized. We don't know. Everything is fake, randomly initialized to 0. What it has to be? It has to tell that what is the best way to go to your terminal state. What is that? 1, 2, 3, maybe 1, 2, 3. So that's the number that we want to be placed over here. Right now it is 0. It's not able to even tell anything about any state. Everything is wrong. But it's initialized. K equal to 1, V1, understand. You need to understand what? You need to understand one fact, that these values are going to be computed from where? V1 has to be computed from V0, which was your previous thing. And what was that? 0, 0, 0, 0, 0. Fine, that is wrong. Fine. But V1 is going to be computed from there. How? Let us compute V6, 1. V6, 1. There are 4 directions in which you can go. Remember, what are the actions? North, south, east, west. Which is north? North, south, east, west. So north, you may end up 2. 2th is your state is 2. 10, 7, 5. 2, 10, 7, 5. You want V02, V010, V07, V05. No, yes. Sujit, you have any question?
No, sir.
No, sir. Good. Sujit, you are crediting or auditing?
Crediting, sir.
Crediting. Okay. V0 we are going to utilize, but I am saying that to compute V16, you require V02, V010, V07, V05. But all of them are not directly going to be added. V02, if you take one step, what is the reward that you are going to get? -1. So -1 plus gamma. Gamma is 1. V02. And with what probability? 5/4. Sorry, 1/4. Similarly, for this guy, -1 plus V010, 1/4. -1 plus V07, 1/4. -1 by V05, 1/4. You add all of them, you are going to get a -1 value. That is why you have got a -1 value over here. -1 value over here. You do it for all the states. If you wanted to know something from this guy, left, right, top, bottom. So this guy is going to be dependent on V8, of 0, V8, 0, V8, 10, V8, 10, V8. Compute, do the average, and you are done. That is why you have got a -1 over it. Now you understand your previous thing was 0, 0, 0. Now you started to get some value. Soon you will converge into the correct direction. Now, V2 is this. How I have got a V2? V2 आया कैसे? -2. Same thing. It is going to be 2, 5, 7, and 10. But V2 1, V2 7, V2 this, and V2 this, but taken from this guy, not V0, but V1. You just obtain V1 2, V1 10, V1 7, V1 5, same probability, something, something. You multiply, you are going to get -2. You have got a value -2. You may ask, sir, if you are at this location, if I go south, what will happen? Loop it. If you go south, you will be here. That's the logic of your game. It can be anything. You may give some other reward, some loss, I don't know, but here it is that you are looping. So here you see it is V14, V214 will be V113, V110, V1T. V1T will be 0. V1T, because that's the final place. And that is V114 again. V214, V114. Because here it is looping. This is a very simple DP. It's being solved in the way of DP, and for each and every, just you just apply for all states. You have one matrix, and you are computing the value of all these state values within this matrix using the previous matrix and applying this simple formula, neighborhood and all. If you take this action, this action, this, all possible actions, you keep on averaging, you're going to get this value. Keep on doing. Now, that is so what now I'm going to show you that what we have done, we have understand how to get policy being evaluated. Now let us see what's going to happen now. The same thing, same equation, same diagram. What was that game? Grid game, single game. Actions, 4 actions. So everything remains to be the same. Just I am going to show 2 things for you. One thing over here. One thing over here. This is policy. This is value. This is policy. Just we choose first the random policy. You can see this is my random policy. With respect to that random policy, I have got random initialized values VK000. They may be wrong. Okay. From this, okay, first I have got a policy. I've got a VK or V0. With this, can you compute this? Yes. Once I compute this, what does this mean? This means that if I look this location, it is saying that I am equally probable if you go here, 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 or here, because everywhere it is -1. There is no bias. So the corresponding policy over here is this. Yes, but if you are here, where can you go? Where you should have to go? Do you want to go here? You want to go here? Because you have got this value. So if you are at a location, left, right, whatever, I mean, north, south, east, west, wherever you are getting the minimum, try to move in that direction. Everything remains to be the same. You are equivalent. So with respect to this, if you apply greedy policy, what is greedy? You just look left, right, north, south, east, west, whichever is the best, move in that direction. That's the greedy thing. You will get this policy. Please check. At this location, you will just go this direction. You check. Go in this direction. So after one iteration, it actually understand very little, but at least it got that for this guy and this guy and this guy and this guy, I know. But for them, it is almost same. That is pi 0. This is pi 1. Don't do anything, because we have got this. Can with this, can you get k equal to 2? Yes, can get. Again, you apply this. Now you see it started to get better policy. More and more guys started to say, hey, here you can go in this and this. Only diagonal, that is random. That is pi 2. Anyways, you are not computing pi 2. At any point of time, if I give you a value function, you just apply greedy decision and you will get a greedy, you will get a policy. If I give you value function, I have given you the policy, by the way. You understood? If I give you a value function, who is this value function? Value function is like Ramkrishan Paramhans or someone who is helping you. Hey, you ask, in this direction, how much? 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 And which one is the best? You move in that direction. That is your policy. Basically, that is a greedy policy. If I give you a value, it is equivalent. I have given you the policy, because policy is a greedy policy. Okay. So now you see that pi 2, pi 3 is slightly better. And then k equal to 3, 4, 5, 6, 7, 8, 9, 10. This is k10. That is v10. You see both of these policies. And then you do it for k equal to infinity, it got converged. Even the value slightly got changed. You can see k3 is this, k10 is this, k infinite is this. Values are slightly got changed. Policy is not changing. Policy got saturated at some point. Value maybe keep on changing, but doesn't matter. Because at this location, it is saying, at this location, it's every time saying move in this direction. Whatever happened at this location, move in this direction. At this location, it is saying here or here. I'm not getting any better clue. Please raise your hand if you all can understand. This was an important concept, very important concept. If you understood, please raise your hand. Sujit is Chinmay, Soma, Deepti, Prashant, Sujit, Priyanshu and Prashant. Okay, you all understood, right? Now, हाँ पूछो.
सर यहाँ पे जो हमारा वो वैल्यू फंक्शंस आए हैं वो तो रैंडम पॉलिसी के अगेंस्ट आए हैं.
हाँ, हमने नहीं सुनिए रैंडम पॉलिसी बदलती गई ना. आपको दिखाया रैंडम पॉलिसी शुरू में चुनी थी.
हाँ.
जैसे जैसे मैंने वैल्यू फंक्शन पे चेंज करता गया, वैल्यू फंक्शन पे आइटरेशन करता गया, वैल्यू फंक्शन आइटरेट होते टाइटरेट होके कोई अच्छे वैल्यू फंक्शन पे आ गया, तो पॉलिसी लगातार बदलती रहती है. यही मैंने आपको दिखाया.
सर तो अगर मतलब ये प्रूव कर सकते हैं कि अगर बीच बीच में हम लोग ऐसे पॉलिसी भी चेंज करते रहे तो वो एक्चुअली में पॉलिसी भी कन्वर्ज होगी अपनी.
अभी बताता हूँ वो वाली बात भी, बट ये प्रूव्ड है.
ओके सर.
प्रूफ है डीपी में, पूरा प्रूफ किया हुआ है. डेविड सिल्वर लोगों ने किया हुआ, जिन्होंने ये सब ब्रांच स्टार्ट किया था. बाय द वे, दिस इज ट्रेडिशनल आरएल. ठीक है, ये ट्रेडिशनल रेनफोर्समेंट लर्निंग में वो इस तरीके से सॉल्व करते हैं. अभी हम बताएंगे कि क्यों नहीं हम लोग ऐसा करते, लेकिन इसका प्रूफ अवेलेबल है. कि ये रियल फंक्शन या ऑप्टिमल, इट्स बीइंग रिटन ओवर हियर, ऑप्टिमल पॉलिसी पे कन्वर्ज कर जाएगा।
ओके सर।
अच्छी बात है। अब आते प्रियांशु शुभम के ही क्वेश्चन पे। ये तो k इक्वल टू 10 पे कन्वर्ज हो गया, 8 पे कन्वर्ज हो गया, बिकॉज योर गेम वाज वेरी सिंपल। इफ योर गेम इज वेरी डिफिकल्ट, it's not converging. Theoretically it has shown it will converge, but practically if it's not converging, and several times it won't converge because your games are complex and so on. Not only that, if your state and if your state and action space is very big, this matrix becomes very, very big. You cannot store, you cannot work. It becomes infinitely large. In the continuous action space, it won't work. But first, we need to understand that if it is happening and work like this, what is being done? So we start with some pi random. We get our value random. Then we iterate v12. So v1, then v2, and you say that I'm not changing the policy, pi r, I'm not disturbing the policy. v1, v2, v3, v4, and from this v4, I change the policy. So the point is that it's also not advisable that after every value iteration, you switch your policy, because as soon as you switch your policy, your value function will again be changed. You again need to compute so many things, because you understand the pi is going to be multiplied with them, and your pi was pi by 4, 1 by 4. You keep on using that 1 by 4 here. Although internally it is switching the policy, you don't switch. Your value function keep on changing. First value function, second, third, fourth, fifth. After 4, 5, 6 steps, switch your policy. And then again find out value function 1, 2, 3, 4. So that is value iteration, and that is policy switching. You iterate over value function. After some time, you switch your policy. This is justifiable, and the way Priyanshu was saying, I mean, I guess that's what he was trying to say, that can we at all switch our policy? Yes, switch after some time. What is that sometime? That depends upon your game, your memory, and so many things, and the computational constraints. So given any policy pi, evaluate the policy pi by computing the value function. Keep on iterating over that value function so that its corresponding greedy policy got saturated, and then improve your pi to pi dash. No? Yes? Huh? So this is policy evaluation and policy improvement. Policy evaluation, you give me the policy, I will tell you v pi. And policy improvement means that pi dash is better than pi. And it is being guaranteed that the pi dash is going to be better than pi if you are applying the constructs. So we have some random policy. Corresponding, we have some value function. And so this is value function got converging. This is greedy policy that's going to be converging. So given this policy, I've got a value. For that value function, I find out the greedies. So I can do slightly play with this some amount of, some policies. Iterate over here, got the value, got the next pi. For that pi, again I got a value, again that pi, again value, again pi, again value, again pi. That is policy evaluation and policy improvement. Using dynamic programming, you can solve it for simple programs, simple problems, simple games. And it's definitely going to be converted. It's not going to take good, not more than some amount of time. Whatever I have covered, that simple grid algorithm, simple grid problem, you can code directly. Straightforward code is there. No deep learning, nothing. So you have a pi. You evaluate, you will get V. You take a greedy decision, you get a pi. And then you keep on doing. You slightly iterate over V, keep on changing, and then go back to some greedy pi. And keep on doing. And that is called as improved to be converged. It's being proved that it's going to be converged into some optimal policy. I have written it wrong that it is a policy iteration. This is value iteration. You are iterating over value function, and from that you are getting another policy. Policy iteration we will cover separately. That's called as policy gradient also. So they also call it as policy gradient or policy iteration or value iteration, but essentially you are iterating on values. But in some senses, you can also say that I have got a pi, then I have got pi 1, then pi 2, then pi 3. So that's in that way also it is a value iteration. So if I give you value function, you have got a pi corresponding, and vice versa. So you can come from here to here, here to here easily. That's what is the two-way being shown. And finally, it's being said that you will be, once got saturated pi stick, you will get pi stick and V stick. So Q stick S comma A is this, nothing new. It's the expected value that if you at state S, if you take A, all the places where you can go, for all of them you get the expected value, which is R plus gamma times max of all of them, S comma A. We have shown in our last lecture. And what we have shown, why we have shown, because both of them, Q stick and V stick, both of them are actually following the Bellman optimality. Max and so on. So they are actually being shown and proved that they are actually following the Bellman optimality. And you can solve it recursively. But the problems with DP solution, this is a DP solution. You need not to do anything. Just take your game, take your MDP. You require all these MDP, by the way, because this is called as a model full algorithm. Because you require that P's, R's and everything need to be properly with you. As shown above, the Bellman equation can be used to solve the optimal Q value function, evaluate and improve, and so on. This optimal solution is proved to be converging and easy to compute, but not scalable. And as we all know, that state, how many states you can have in an Atari game in which one frame is a state? So in a frame, there may be m cross n pixels. So m cross n different positions. And for all of them, 256 different possible values. So what total number of states that you can have will be 256 for first location, multiplied by 256 for the second, then multiply 256 power. So in most of the places, your state is going to be very big. It's going to be very, very big. In fact, your A's can be limited several times. If you are playing simple Atari game, left, right, top, bottom, or maybe few more angles and so on. But several times your action, if it is not discrete, then you have a continuous action space like robotic hand. How far, how much it has to move. It's a continuous space. In continuous space, you are having infinite actions. So you cannot solve it using these types, because your state action pair, you are going to have huge amount of state action pair, and for each and every state action pair, you cannot work separately. Yeah, so today we wanted to discuss up to this. With this, my suggestion will be that please try to consume whatever we have covered today. Publicly lectures are anyways available. All these things are publicly in that lecture series is being available in the very in exactly the same format. Finish it up, because in the next lecture we will directly show you the deep Q learning. If you understood all those things in in half an hour, I can explain the whole deep Q learning. Very simple algorithm. But you need to make your frame of mind. Your frame of mind need to be in such a way so that you absorb all that stuff that we have covered, that we are not learning MDP. We are not learning this, we are not learning that. What you are learning a pi, but now you are not even learning a pi. You are iterating over values, and then greedy solution is actually the your policy. And now I will say that, hey, you cannot apply that DP solution. Then you require someone who, instead of computing factorial 55, factorial 274, he is directly going to tell, hey, factorial 274, I am telling you it is this. How can you check? Factorial 273. He will also going to give you something. Multiply it with 274. See whether how close, how far they are. So you started to approximate, instead of computing the value function or Q function, directly approximate that thing. And who is the best approximator for us? Best approximator we know is neural networks. So that's why we are going to use neural networks to approximate Q function for us, and that is why it is called as deep Q learning. Okay, that is the thing we are going to see in our next lecture. This week Daksh may be going to share certain reading material or maybe lecture material, and as well as he may be covering certain things. So make yourself available to attend those sessions. ठीक है, any questions? कोई doubt? कुछ पूछना है किसी को? प्रशांत, प्रियांशु, सुजीत, सोमा, दीप्ति, आवाज आ रही है? दीप्ति, आपको आवाज आ रही है?
Yes, sir.
Yes, sir.
आपको आ गया समझ में?
Yes, sir.
सुजीत, आपको कोई इशू?
No, sir.
No, sir. Good. So please cover this stuff, because next 2 or 3 lectures we will be directly now moving. So RL basic हो गया, सीधा अब अंदर जाना है डीप लर्निंग में, कैसे ये सारी चीजें डीप लर्निंग के थ्रू सॉल्व होती हैं. थैंक यू.